I don't know if hers is as good as mine. Okay, so we've added an objective since the camera stopped running to see how fire reacts to different concentrations of oxygen. And I'm going to hand the camera over to Clay, who will surely do a better job than I've been doing. We've definitely seen burning increases with an increased concentration of oxygen, no doubt. And let's take a look at our temperatures. I don't think this is going to work at all because I'm going to switch that into the fall. But the one that is labeled E is now reading 27.5 degrees. This one is now reading 28.5 degrees. So they really, relative to each other, they didn't really change. Because if this one is 27.5 degrees, this one's 28.5 degrees. Yeah, I don't think that we got enough gas into these giant bags. But smaller bags don't hold the thermometers, so I don't know. This experiment needs different materials, and there's really not much hope for it. Sorry. But back to our oxygen and fire experiment. We've got a great objective, but now we need a conclusion. So if our objective is to observe the effect of how fire reacts to different concentrations of oxygen, what conclusion would you draw from what you observed?
In the presence of a high concentration of oxygen, a flame will grow brighter.
Okay, so increasing the amount of oxygen increases the burning. We definitely already essentially wrote that here in number 6. So even though number 6 is this, you're really going to write the exact same thing for your conclusion. If you have a lot of oxygen, you're going to have brighter, faster burning. Same basic thing. And I'll give you a minute to finish making sure you've got everything. Does anyone have any questions about any area of this worksheet? All good? Okay. Take out your homework. And we'll talk through some of the concepts from this week's reading. Make sure you're all ready for this test, answer any questions, and do the study guide together. So, this chapter talks a good bit about global warming, which we hope to kind of demonstrate the effect of greenhouse gases such as carbon dioxide in our completely failed experiment with the thermometers in the bags on the window. But just like you saw that the concentration of oxygen increasing causes burning to increase, the same holds true. If we really did get a bag full of carbon dioxide and a bag full of regular air, and we put thermometers in them and we did that experiment, we would definitely see that a bag full of carbon dioxide would trap heat more than a bag full of regular air, because carbon dioxide is a great trapper of heat. It's a greenhouse gas. So is water vapor, ozone, and there are a few others that are great at trapping heat. Without them, we would be freezing or non-existent or dead, because the Earth needs to trap some of the heat from the sun and keep it here in our atmosphere, and otherwise it's completely reflected back up to space. So carbon dioxide is really good at absorbing energy from sunlight, infrared light heat. Increasing its concentration will increase the temperature of air. How to say this? Global warming increasing the amount of carbon dioxide in our air through man-made means, pollution, industry, cows even, and breathing, and humans, and well, methane is a byproduct of lots of things like cows being alive, and other things. But all of our industry, our pollution, our lifestyles have, without controversy, increased the amount of greenhouse gases in our atmosphere. But where the controversy lies is that really going to change the environment? If we do that in a little plastic baggie, we see that it does trap heat, it does increase the temperature inside the little baggie. But on a global scale, with so many other variables that we can't control like we can in a lab, is that going to change the temperature? There's a question on the test that literally, I think I even tell you, I told myself in my notes to read the question on the test to you. Here, has the Earth's temperature increased significantly in the past 80 years? That is word for word on your test. And I'm not going to tell you you're wrong if you hold a different opinion than the author of the textbook, but you need to support your opinion. So if you think that global warming is a threat that's really happening, cite some evidence. If you think that it's not, cite your evidence. But I'm not going to mark you wrong just because you don't give the answer that's the answer in the test you give, as long as you do. But let's talk a little bit about. So since the late 1800s, the Industrial Revolution happened, factories have been built, and we've certainly produced a lot of carbon dioxide, water vapor, as they increased a bit, in the atmosphere because of the burning of fossil fuel and other things. In the last 80 years, the amount of carbon dioxide in our atmosphere has increased rapidly. If you look, and I should get out, if you look at the graph in your textbook, there's everywhere. If you look at page 37, I think this is a really interesting thing to consider, because the way graphs are presented is huge in the way that you're convinced about the evidence. And it's easy to use the scale of graphs to make something look like something it's not. That's not to say that I'm saying global warming is or is not happening, but I am saying that he's right to consider the graph and look at the range of the graph. So, if you look on page 37, you see a graph of the concentration of carbon dioxide versus the year. And you can plainly see that the concentration has gone up from 280 parts per million-ish to maybe 380 parts per million-ish. So that's a change of 100 parts per million over, 105 years, which is a significant change, a measurable change. Then if you look at the temperature change over that same period of time, you see it going all over the place, right? But it looks like there really is an upward trend, right? I mean, you can see starts down here, goes up, continues up, has a real spike here. I think that's the summer I went to college, no air conditioning, it was really hot. But anyhow, you can see that it does end up way up here, started way down here. But you've got to look at the scale. Okay, this is a negative 0.6 degrees Celsius from normal. Normal here is right on the 0 line, normal temperature. And this is a positive maybe 0.1 degrees Celsius. So the change there is about 0.7 degrees Celsius. The range on the graph is small, so it makes it look like it's jumping around all over the place. If you flip a couple pages here, he shows the same graph with a different scale. Exact same data. Right here, the temperature over the same years, but the scale is different. And it looks almost like a flat line. Right? It hovers right around the 0 mark. It looks much less dramatic when the scale is very different. So it is important for you to really, when you read a news article or you read a scientific paper, you need to look at what it's really saying and how big the numbers are that it's talking about, or how big the if you're reading a psychological study, how big the population is that they're studying. I mean, if they say, oh, this happened to every single person we studied, but they only studied 5 people, that may not be that significant. You've got to look at what they're really saying with their data, because of course scientists tend to be biased toward the result they're hoping for, and they may purposefully skew their data to look a certain way.
No, Mrs. Matthias?
Yes.
How did they find in figure 2.6 how they say 0 is like the normal temperature?
Yeah.
How do they determine that it's like, so is it like colder in 1880 than normal?
Yes.
Is that what it's saying?
They're saying 1880 was colder than normal.
Okay.
Isn't there like a
yes,
set
defining
number
normal
for?
is interesting. There is also a shift in there, just like when we hand a lab off from one person to another, that can cause error because you may read the thermometer a little differently than I do, or line up your eyeball differently, or have more or less experience reading the thermometer than I do. So just like that, there was a shift in how they collected the data. We went from averaging a ton of land-based stations data to collecting it from satellites, so we could get not only land-based data but also over the ocean, the average temperature. So that graph, the graph there, the data was collected differently over different sections of the graph, which can definitely include something to consider when you're looking at the graph. Now, I'm definitely not here to debate, is global warming happening, is it not happening? I think that debate is just really emotional for people and not what I want to do with my 20 minutes that are left. But you also have to consider there are other factors that are releasing greenhouse gases, such as volcanic eruption. There are natural warming and cooling cycles that Earth experiences that we know have happened over the historical past. We can see that even from before good data was kept because of information that we can get from things like tree rings. We can see that there were droughts, hot periods, cold periods, and we know now we're just starting to understand how the ocean factors in. The ocean is a huge amount of water. Water can absorb a huge amount of heat, right, Clay? I mean, we learned about that in chemistry. Water can just absorb heat and barely change in temperature at all. So the ocean has these big currents too. So it can absorb heat at the surface from the sun, and then that heat is like carried by these currents, and it can take a really long time before it comes to the surface again and is able to be released back into the atmosphere. So the ocean warming and cooling can have a huge effect on the climate that we don't necessarily see instantly. Chris?
So sometimes while you go swimming in the ocean, then you're swimming in a really warm part, and then all of a sudden it's really cold.
That can be something, but I'm talking about deep ocean currents, like on a large scale. Because when you're swimming in the ocean, you tend to be in a shallow area. Even 40 feet is shallow for the ocean, you know what I'm saying? And yes, you experience currents and wide variations in temperature even there, because the ocean is just, there's so many factors. But in the deep ocean, we only are just beginning to see where heat and stuff is moving in the ocean. There are really interesting studies actually going on now about where stuff is moving in the ocean, but I don't want to go on a rabbit trail. But ocean currents and the way that the ocean stores heat is also something that we have not really factored into our thinking about global warming. So it can be a very complicated problem. But go into the test prepared to give an answer about why you do or do not think that the Earth's temperature has significantly increased in the past 80 years. Is 0.7 degrees Celsius significant? So make sure you're prepared to answer that question. I'm not going to give you an answer there. So if you have a few hot summers, a few warm winters, a cool summer, a cool winter, you can't assume that climate change is happening, because regional weather, which we'll study a lot this year, and overall global climate are very different things, right? I mean, a hot summer for us may be averaged out by a cool summer in California. You know, a terrible winter in Minnesota might be averaged out by a very mild winter in Poland. The Earth as a whole is not just what you experience. It's much, much bigger than we really account for in our own personal experience. And it's right for scientists to be concerned about pollution, carbon dioxide, nitrogen, and sulfur compounds, not just because they may contribute to global warming, but also because of things like acid rain. These pollutants are things that cause acid rain. They can cause breathing issues. In London, during the Industrial Revolution, I mean, like, the walls were black because of the amount of pollution. When I went to China 3 years ago, you could literally stare at the sun because the pollution is so thick that you can look right at the sun. It looks like the moon. You can feel the pollution touching you. It's so thick in China. So pollution's a huge problem on a global scale. That doesn't mean that I'm saying, oh, global warming is going to exponentially increase and it will suddenly be like 10 degrees Celsius hotter. But what I'm saying is, God has given us dominion over this earth, and we're really polluting it on a global scale. So whether or not global warming is happening, it is the responsibility of Christians to be respectful of the earth that God has created. So just because you think or don't think that global warming is happening, you still do have a responsibility to be a steward of the environment. Not going to the controversy, but it is important to think about your impact on the world. Now, let's get to the math. So, parts per million. When we looked at that graph just a minute ago, on page 37, the scale said that it was telling us about the carbon dioxide concentration in ppm, parts per million. There is a test question, 2 test questions actually, about parts per million. I'm writing on this board for a minute. So parts per million is just something that's going to test your knowledge of both percentages and fractions a little bit. But I'm going to give you kind of the Cliff Note version of what you must know for the test. And then just kind of, okay, that's as much as I can reach anyway. So, parts per million. Anyone know the definition of parts per million? Is it? It is. So, when you look at the study guide, for example, you've got 5 definitions right here, and they're all 5 on the test. Please memorize them. And parts per million is one of them. So, anyone to say?
The number of molecules or atoms of a substance in a mixture for every 1 million molecules or atoms in that mixture.
Okay, the number of molecules or atoms of something per every million total molecules or atoms. Alright. So what does that mean? If I had a box full, of course, of 1 million marbles, that might be a vast box, but if I had a box of 1 million marbles, and one of them was black and the rest of them were white, how many marbles per million are black?
1.
1. So, if one marble is black and the rest white in a box of 1 million, then I would say those marbles are 1 part per million black. Okay? That That means one marble in a million is black. 1 in a million. 1 part per million. Okay? So, then, when we talk about concentration of things like air, like earlier you told me that air is essentially 21% oxygen on average, right? So we're used to talking about percentages. When you get your grades, or we talked about relative humidity last week, we talk about percentages. And percentages are something that's comfortable. So one of the things you need to know how to do for the test is convert from percentages to parts per million. So let's think about it. Well, what does 1% mean?
1 per every 100.
Exactly. Well, 1% means you got 1 out of 100, right? They say 1% of people have 9 toes. I don't know, that is just made up in my head. But that would be 1 out of 100. 1% means 1 out of 100. Well, if I say 1% of the marbles are red, then that would be 1 out of every 100 marbles is red. But I've got a million marbles. So what part per million is red? How do I convert 1% to part per million? So we know 1% equals 1 out of 100. Well, what does that equal when you have 1 out of a million, Joseph?
It equals 10,000 parts per million.
Okay, so one easy way to do a good job on this test is to say, I know that 1% equals 1 out of 100, or 10,000 out of a million. And memorize it. I'm going to show you the way I think this through. So, if I know that I've got 1 out of 100, and I want to turn that into how many out of a million, here's what I do. I say I want this bottom number to be a million instead of 100. How many zeros did I have to add to make that happen? 4. So all I have to do is add 4 zeros to the top so that I'm balancing it and getting the same. And that means that 1 out of 100 is exactly the same as 10,000 out of a million. Okay? See how I added 4 zeros to both to find out essentially parts per million. I added my 4 zeros to both. This is essentially a test question. 1% in parts per million. So 1% is 10,000 parts per million, because there's 10,000 out of a million. That's the same as 1 out of 100. You can see that those things, because I just added those zeros and I made it a different color so you could see. So let's check our understanding. By doing a quick little problem, you can talk to your neighbor about it. Our water, another made up number in my head, so don't go panicking, has 0.00052 part per million lead. What is that in percentage? Good. Thank you for being very quick. Anyone who's not as quick as that, which I don't even think I am, should just try that problem on a scrap of paper or the back of your lab sheet or something. I'm not going to collect it or anything, but make sure that you can do that while I keep it. I'm going to write a conversion factor right here that you can memorize, and that's the only thing you're going to need to know to get the problems in.
Guys,
Uh-huh.
you got your knock like a couple minutes ago.
Oh, great, thanks.
Just saying.
That's not good. Okay. The point, since you've had a minute, and I don't have any more minutes apparently, is that 1% and 10,000 parts per million are exactly the same thing. Okay, it's a conversion factor. It's like saying 2 over 2, which you know equals 1, right? Multiplying anything by 1 just doesn't change it, right? And 2 times 1 is still 2. So multiplying by something that equals 1 doesn't change anything except your unit. So if I want to cancel out parts per million, I can just multiply by this. 1% over 10,000 parts per million. That cancels out my parts per million. Cancels out my parts per million and gives me percent. So all you have to do is divide that number by 10,000. If you need to convert the other way, you just use the same conversion factor flipped over. 10,000 parts per million is the same as 1%. Just like you can flip 2 over 2, it's still 2 over 2, right? And it's still 1. You can flip it over, you can flip conversion factors right over, right? You can say 12 inches is a foot, you can say 1 foot is 12 inches. You can flip your conversion factors right over. So if I were going the other direction, from percent to parts per million, I would just use this one. So these two green boxes right here are the two things you need to know to convert on the top. So don't panic when you get these problems. You're going to use that one or that one just to cancel your unit. So Joseph, tell us that answer again.
0.0000000052%.
Is that 7 zeros?
Mhm.
Okay. And then my part per million canceled out. Because one's in the numerator, one's in the denominator, and I just keep a percent. So 0.00052 part per million equals 0.7052. I mean, this is 7 zeros right here, just so you know, percent. Just to make sure you guys can do that. We briefly touched on how ozone works. Ozone is a greenhouse gas, but it has another function. Ozone is actually 3 oxygen molecules bonded together. Do you remember this double, triple? I can't remember it anymore.
No.
Well, they're not single bonds, but anyhow, here's what happens. They've got their bonds here, 3 oxygen atoms bonded together. When the dangerous UV light comes into our atmosphere and strikes an ozone molecule, the kind of ultraviolet light that can hurt us has just the right amount of energy, but it also destroys ozone. Okay, it breaks their chemical bonds. So it, splits their chemical bonds apart. But in doing so, the ozone absorbs the ultraviolet light. So ozone molecules get destroyed when they absorb ultraviolet light. They're broken apart. Now the oxygen atoms are still there, but they're broken apart, not ozone bonded all together like that anymore. And so they absorb the light by breaking the ozone apart. It doesn't get to us to damage our skin with ultraviolet radiation that can give us cancer. Ozone supply is replaced naturally in the ozone layer, so even though it gets used up, it also gets replaced so we don't run out. Of course, there's a hole in the ozone layer, which I think you can read about in your textbook. The ozone layer is up high in the atmosphere, which we'll talk about in a week or two, where we don't go, right? We don't hang out where the ozone layer is high up in the atmosphere, which is good. Why? Hold on, who do I nice? Oh, Ava or Elise? Ava. Why is it good that we don't hang out up there where the ozone layer is? It is. Ozone is poisonous to us. So, if ozone is a ground level pollutant that we're down here breathing, it's bad for us, it's dangerous for us. but when it's up there where we're not exposed to it, it's helping us by absorbing ultraviolet light that can hurt us, but not being consumed by us and hurting us. So it's great.
Mr. Hart, what produces ozone?
Lots of things. In fact, that weird smell that you smell, like when there's about to be a lightning strike, have you ever smelled that? That's not good. Like, it's time to move if you smell that. No. Or, like, if you produce a huge amount of static electricity, can you smell it, kind of? That's ozone. Yes. The smell of ozone is very unique. And when there's a lot of static electricity buildup, like during a lightning storm, or when a big static charge is built up and you're about to shock someone, ozone is produced and you can smell it. Or you super rub a balloon on your head and create a lot of static electricity, you do produce some ozone there. But that concentration is low. It's enough to smell, but not enough to hurt you, so don't panic. But ozone is poisonous in enough concentration, but not at super low concentration. There's also a test question which I personally missed because I wasn't interested in it, so I didn't pay attention to it, so I'm going to tell you about it. Cars have catalytic converters. What pollutants do catalytic converters reduce? Who have I not talked to? Oh, I talked to all you guys. Oh no. Eugene? Carbon monoxide. Catalytic converters reduce the pollutant carbon monoxide. So that's on the test. I definitely did not notice that when I read the chapter, and I'm not interested in it and don't know anything about cars, so I had no way. Just lost it in there. Carbon monoxide. So make sure you know that. What time is it actually? It is 1:06. Alright. I might actually make you guys a video of all of these. You may ask your mothers to allow you to see the answer key if you haven't checked your work on the study guide. But please don't look at the test section, which I hope has been removed from your study guide answer key.